Hello students, let us continue with the properties of coherent states. So I told the coherent state are the eigenstate of annihilation operator. So you have a annihilation operator, alpha is a coherent state. When you operate this one, you get the eigenvalue alpha. Now coherent states are special states. They form the basis for continuous variable quantum information. Now, if I operate on a zero state, this is also called vacuum state. So this gives me zero. Now, these states are trivial eigenstate with a zero eigenvalue for annihilation operator. Now, I want to create this coherent state by applying some operator d alpha on this vacuum state. Like we can create applying different states or operating a dagger or a on state n we have seen in the quantum harmonic oscillator. So is it possible to create coherent state by the application of displacement operator on a vacuum state 0? Now, why I call this is a displacement operator, the meaning will be clear in short. Now, say this operator, I define d alpha. I define d alpha as e power alpha dagger minus alpha star a. Now, this operator is unitary. If I say d alpha, so what will come? If I take this one, so this will come alpha star a minus alpha a dagger, and you have a e alpha a dagger minus alpha star a. So this cancels out, e power 0. So this is your I. So displacement, this is a unitary operator. When operates on vacuum state, you create coherent states. So this is d alpha. D alpha is unitary. Is unitary. Similarly, we can show that d adjoint of d is equal to, just now I return, e alpha star a minus alpha a dagger. This is equal to d minus alpha. So we can say d alpha is equal to d minus alpha. That means what? That means if you displaced by alpha and then you come back minus displaced again by minus alpha, you reach the same state. Now let us use a BCH formula. We know we have our operator. We have our operator d alpha is equal to e power alpha a dagger minus alpha star a. Now I want to write this using the BCH formula. So use BCH formula. BCH is the name of scientist. The name of scientist Baker, Campbell, Hausdorff formula. Now this formula says e power a b e power minus a is equal to b plus ab plus a commutator of ab 1 upon root 2 plus 1 upon root 3 commutator of a with commutator of a b and so on. We can write like this. Now here I defined my operator A as dagger, this one, alpha star A minus alpha A, and I defined my B as an operator, say annihilation operator. Now, if I compute the commutator A and B, so what will come? Commutator of A, alpha star A minus alpha A dagger, and B is A. So alpha star A with A alpha is the complex number. So A with A will give you the 0, and now minus alpha A bar A. So this, if you solve this one, it comes out the number, a complex number. This is a number. So if I use this value, that means that my operator commutator AB commutes with A also, because it is a number, and it commutes with B also. So these all are numbers. So I can write my EA. EA is what A I defined this one. That means my D dagger alpha, B is my A, and this is my minus A will become alpha. This one D alpha is simply equal to B is A, and AB is equal to alpha. So this is my definition now. So why I named this as this operator as a displacement operator? You can see now. So D alpha A D alpha is equal to A plus alpha. That means this operator, okay, displace A by amount alpha. That's why it is called displacement operator. So simply you can also write D alpha A D bar alpha. You can show this is equal to A minus alpha. Okay. So now let me write this operator in one more alternate form. So say I want to write this operator in some alternate form. So I have D alpha equal to E alpha A bar minus alpha star A. And now I use one more formula called Jason-Hawes formula. Jason-Hawes formula, and this formula says E power A plus B is equal to EA EB E power minus half AB. So again, I define my A not like this. I define my A, I define alpha star A minus alpha A bar, and B I already defined as A. Now AB, commutator of AB is alpha. So whenever your A commutes with AB, commutator of AB, which is in this case, and commutator B also commutes with AB, in that case you can use this formula. Now let us use this formula. My operator is D alpha. So D alpha is equal to E alpha minus alpha star A. Okay. So this is now, so this how can I write now? So I can write say EA. Okay. So I write here. Sorry. If I say my A is here. If I say my A is here, alpha A bar, And if I say my B is here minus alpha star A, okay, then what will it become? My commutator becomes commutator of A and B. Then my commutator of A and B becomes what? My commutator of A and B becomes now alpha A bar minus alpha. So this is alpha dagger minus alpha star A. So this gives me mod of alpha square, and this is your A dagger minus A, and this is equal to minus A, so minus, so A is minus plus, so again alpha square, so this gives me the alpha square by 2. Okay, and this commutes with A as well as B because this is a number, complex number, so I can always use this formula. And now I can write this, say this operator E alpha A dagger minus alpha star A, I can write is the E alpha A dagger using this formula, E minus alpha star A, and this is the mod alpha square, so E upon minus alpha mod square by 2. So this is the another way of writing your displacement operator D alpha is E power minus alpha mod square by 2, and then you have a E alpha A dagger E minus alpha star A. So this is the another form of writing displacement operator. Now I can show with this displacement operator that coherent states are the eigenstates of annihilation operator. I can show with this formula. So we have already seen that d bar alpha A d alpha is equal to A plus alpha. We have already proved this one. Now what I do, I apply here, say I know my coherent states are given by d alpha. Applying on vacuum state. So when I apply this one on vacuum state, you get alpha. Now let us apply A alpha here, A alpha. So A alpha will be A d alpha, this one, and d A d alpha value I can get from here. Okay, if I operate d alpha here, d alpha d bar alpha A d alpha, this will be what? This will be d alpha A plus alpha, A plus alpha. Now this is the unitary, so this become 1. So my A d alpha is simply d alpha A plus alpha. So now this becomes A d alpha, I'm replacing from here, d alpha A plus alpha, and this becomes 0, 0. Okay, and now we know when A operates on 0, you get 0. So this term will become 0. When A operates on 0, this term becomes 0. So you have only d alpha, alpha d alpha 0, and d alpha 0 is nothing, your state alpha. So I told this is the alpha quantity state is the eigenstate of annihilation operator. Now, what we can do more with this one, I can also use this d alpha, and I can write this current state as a superposition of uh, uh, a simple harmonic oscillator states in the basis n. So let us now write d alpha. So we have a d alpha which is equal to e power alpha square by root 2 e alpha a bar or minus alpha star. Okay. Now I want to write say state alpha. So alpha will be again d alpha 0. Just now we have done this one, and now let me operate this on this expression on here. So this gives me e alpha square by 2 e alpha a bar e minus alpha star a on the vacuum state. Now this gives me e minus alpha square by 2 e alpha a dagger. This I can expand 1 minus alpha star a factorial 1 plus alpha star a square upon factorial 2, so on, and this you have a vacuum state. Now whenever a operates on 0, we get 0. Okay, so these all terms will become 0, you will left with only 0. So this expression becomes e power minus alpha square by 2 e alpha a dagger 0. And this this is again exponential, so you can write here as a alpha square by 2 is exponential, so I can write n equal to 0 to infinite e power alpha a, that is alpha power n a root power n, and now factorial n. So I'm writing under root of factorial n and under root of factorial n, which will give you the factorial n, and here you have a 0 state, and this we know already. This is equal to state n. This is the a n under root factorial n on 0 state will give you the state n. So now I can write now say current state cat alpha. Cat alpha can be written as e power minus alpha square by 2, and this is your summation n0 infinite. This is your alpha n under root factorial n, and then you have this is the state n. Okay, so here n is the not a quantum harmonic oscillator state. These are not the excited states of quantum harmonic oscillator here. Here n means the number of photons in a state. So now let us so this is the so we have written as a superposition of alpha as a superposition of number states. And now if I want to find the probability of coherent state to be in n, that is n alpha. So n alpha will come out minus e alpha square by 2 amplitude. So when you operate n here, so you get only alpha n under root factorial n, and if you want the probability Pn to be current state B2 in state n, current state to be in n will be given by magnitude of n alpha square, and if we solve this one, this will be minus alpha square alpha 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 square mod alpha square mod alpha. So this mod alpha square mod square upon this become, and root will disappear and you have only factorial n. So this is the formula for Poisson statics. stat statistics, statistics, Poisson statistics. And now here, lambda value is what? Lambda value is alpha square. Okay, here your lambda is mod alpha square. Now, what does this means? That a laser is what? A laser is the coherent states of photon. And experimentally we can count the number of photon, and that photon basically follow the counting of photons follow the Poisson distribution, Poisson statics. Okay, so in a laser, you have photons are in coherent states, and the number can be counted experimentally, and this experimental measurement shows they follow the Poisson statics. So I will stop here, and we will come some more properties on coherent states in next class. I'm stopping here. Thank you very much.